Hello all and welcome back. So in this video, let's do one more question on space complexity so that your understanding is actually unparalleled and you will feel a lot more comfortable when finding out space complexity of any algorithm going forward, right? So the algorithm is again something which we have done very much in depth, merge sort, okay? There's a small caveat here as well which I want to explain, so please make sure that you understand this properly. Now in merge sort, we have done it multiple times. We are again given a list, okay? We divide and make the calls on n by 2, n by 2. Okay, but again the understanding here is that I'm not going to make this call simultaneously. I'm going to make the call first on the left half. This is going to make the call on n by 4, right? So let me write this n by 2, n by 4, and 1 second. N by 8 and like this. Okay. Once this left subtree actually completes its whole working, so first left subtree is going to run. And now we have seen this a number of times that how many of these functions, right, function calls are going to be in the memory at a time. So in the case when I'm dividing it by n by 2, n by 4, n by 8, at a maximum point I will have log 2 of n functions call waiting, right? Again, this we have seen at a lot of time, binary search, merge sort, time complexity, everything. Functions at max, waiting in the memory, waiting in the memory. So for the recursive call, this is actually something which we know that at least the space complexity is going to be log 2 of n. Okay, because we know that these many function calls are waiting in the memory, right? But if I just quickly write the overall code for your binary search, if I quickly write def, let's say, merge sort, my bad, not binary search, merge sort. So we are, let's say, getting an array. Just writing the pseudo code. So we used to actually call merge sort on left part. Like, of course, we can make this left and right. That should not be a problem. Merge sort on right part. Okay. Now I have actually found out my space complexity for this particular operation, the recursive calls, right? So I know that from recursive call, my space complexity is going to be log 2 of n. That I have actually established because these many functions are going to wait. In the worst case scenario, these many functions are going to wait. And again, in merge sort, so anyway, we don't have any best case scenario as such, right? Always the whole process gets worked on, even if you give it a sorted array. But is there anything else which can cause a bottleneck or which is more memory intensive than this? Well, let us see the same thing. Then we also do the merge function, right? Then we do the merge function where we merge these two sorted half. Now, if I talk about this merge function in particular, what it does is you have this n size array, right? You send it to n by 2 size array, n by 2. It now creates one extra array, which is normally n in size. Normally not, of course, it is n in size, not normally. And then you just copy everything from this, right? So this is how the merge sort actually used to happen. We have again discussed and coded it a lot of time as well. This is your auxiliary space, right? This you are creating to solve your question. This is not just your input part, okay? This is not just your input part. Here again, what you're going to do, what exactly are you going to do is, in this merge function, you are creating so how I can write it is that this is using your log 2n and this is using your n. So if I actually now try to add up the space complexity, I can say that, hey, my space complexity seems to be something like this, n plus log 2n. Again, you can add k in front of them. That is not a problem. You will be using some memory in merge recursive call, some memory in the merge function. That is fine. But again, the understanding is that if I compare for a very big n, let me write this in white. Actually, that is a little bit clear. 1 second. Space complexity. Okay, it's going to be O of. Again, you don't have to multiply them. Please remember and understand this thing. They are happening in parallel. Inside it is not happening. And one more thing you have to understand, let me explain you that as well. So when it gets called, right, when it gets called for, let's say n by 2, when it gets called for n by 2, here also we will be creating this subarray. Here also we will be creating this auxiliary array of size n by 2. But this is going to get destroyed, right? This is going to get created and going to get destroyed. So yes, we are going to create multiple of these subarrays, but at a single point in memory, when I will just come out of all the recursive call, this will be the largest auxiliary space or auxiliary array which I'm going to use. So it's not that they are going to wait in the memory. These n by 2, it's going to get created, yes, but it's going to get destroyed as well. So it's going to free up space, okay? And at a single point, you will just have n by 2, then n by 4, then n by 8 like this auxiliary space, but they are going to get destroyed. So the space is going to get freed up, okay? So on that note, you have to see the maximum space at a single point. At a maximum space at a single point, the peak. And due to that particular reason, this is where the peak will occur, when the merge sort we are calling on the main array, where n size auxiliary space will be created. The n by 2, n by 4 auxiliary space, yes, that will be created, but that will be freed up as well. So I'm not going to consider that. At a single point, the peak space is going to be for the auxiliary space of array of size n. Right? I hope this is clear as well, everyone. It's the same as, let's say you are adding small files, but maximum file which you are adding, right? You are adding, let's say, a file of 1 GB, deleting it, 2 GB, deleting it, 3 GB, deleting it. But when you add the file of 7 GB in your 8 GB pen drive, that 7 GB is the peak. That is what your overall space you want free if you want to just redo all your operations, right? If you want to add and delete all these things again, that is what your space complexity is. In a very similar understanding, you will be adding them because they are parallel, they are happening one after the another. Okay, they are not happening all together with each one of them. Okay. So in that manner, all these n by 2 or n by 4 auxiliary space is going to get destroyed. At the end of the day, I will just have my space complexity like this. If this is my space complexity, then what I can do is, for a very large n is going to be a lot large for log 2n. We have already seen this. For n is equals to 1 million. N is going to be 1 million only, but log n is going to be somewhere around 20, right? If I remember right, that was what we calculated. So 10 to the power 6, something like that. Yeah, something 20, like log 2. I hope it is taking log 2 only. Yeah, log 2. Okay. So if that's the case, then again, I can just ignore the least dominant term. And I think I can very comfortably say that, hey, this is going to be my major term. And thus I can write my major term is n. So let's say now some k space is taken in your merge function, then you can write it kn. Okay, is your space complexity. Okay, because that is going to be the maximum, kn. And now you can very well say that O of n is the space complexity of merge sort. Right, everyone? So again, understand this very, very nicely, that this log 2n, this is in parallel to that. Like first this get used up and then this get used up. Okay, it's the same as this is going to get used up and this is going to get free. So my graph is gonna be something like this. Again, I'm just gonna draw it so that you understand this thing. Okay. I'm gonna have some memory gonna get used. Okay, first recursion is gonna get using some memory. Okay, but this is anyway going to be a lot less as compared to, let's say, when n by 4 auxiliary array gets created. Okay, so this is going to take a peak. Okay, then again the recursion memory is going to be a lot low. You can understand that n by 2 at any point of time for high values is going to be a lot greater than log 2n, right? So log 2n, the recursion space is going to be very less. And finally, I'm going to actually create an array of on space. This is going to be my peak. Array of on. Array of n space. And because I'm just worried about the peak, that is something which I'm going to take. And actually the peak is going to come towards the end, like it's not going to be like this. The reason for that is, once you make all the calls, that is when you're going to work on your merge function, right? So your peak is going to be in the end here. So what I mean by that is, if we see the code again, Once all of them completes their work, right? So inside of these functions, first you're gonna make the calls, then it's gonna make a merge function call inside them as well. In the end, when everything is being completed, that is when I'm gonna use my n array, create an n space auxiliary array, and that is going to be the maximum one. Here maybe n by 2 is created, here n by 4 is created, something like this will be happening. But in the end, once I've gotten all my answers, that is where I will be using this particular thing. Okay. So yeah, I hope that was clear a lot, everyone. Please make sure that you see this. Let me show you this website. Yeah. So now I think these will also make a lot of sense to you. The space complexity, right? If you will see for merge sort, it is O of n only. And I hope now you're able to understand why it is O of n and why all these complexities are n log n, right? So now you will be able to make a sense of a lot of these algorithms. See, bubble sort, insertion sort, selection sort, O of 1. I will ask you to just do for quicksort some algorithm which we have studied. It's going to be a lot easy as well for quicksort. Okay, the space complexity and the overall time complexities also you can find. For some of the data structures which we are going to study going forward, all this will also then make a lot of sense. So you don't have to worry on that anyway. Okay. So yeah, I hope now this sheet will be around 40-50% clear to you. Towards the end of this, you will be able to understand 80% of the sheet very easily. Okay, again, your aim should be to understand the basic principles, not to understand the 100%, because that is not what will get your interviews clear, right? So cool then, everyone. I hope this was helpful. You are able to actually understand the space complexity, different ways to find out that a lot nicely. Again, please make sure that you revise them. Okay, space complexity is also asked, and many times again you have to understand if space complexity is the reason behind your code failing. Okay, so yeah, let's meet in the next video, everyone. Thank you.